Go ahead.
Okay, so this paper is called mm, I'm sorry, I just want to move this menu. Okay, okay, so this paper is called Complex Harmonics Reveal Low-Dimensional Manifolds of Critical Brain Dynamics. So first of all, let me say a few words on what criticality is. Criticality is a concept from condensed matter physics. It's some state of near phase transition between an ordered and a disordered phase of some system. So in an ordered state of material, like in a solid state, we have short range correlation. So we have some kind of order parameter that is short range, and correlations quickly fall off at distance. In the chaotic phase, we have this scale parameter diverges, so we have no so we have no characteristic scale. In the critical state, it's an intermediate phase, so we have long range correlation. So as the system approaches criticality, we get correlations between distant parts of the system. Mm, human brain in particular has been conjectured to be a system in a critical state because it's been able to manage high computational complexity at relatively low energy cost, which is a, mis- a medical mystery so far. And also, neuroimaging shows signs that it has non-trivial topology. So the mm, the synapses are non-local and connect also distant parts of the brain to each other.
So, sorry. So, what's the conjecture? The conjecture is that the state is critical, or the conjecture it's that it is also efficient in making computation. Which of the two?
The conjecture is it's critical. Efficient making computation is just observational factor. So, oh, how we've been able to manage complex computations
Mhm.
is still a puzzle, given that how much our energy our brain consumes is like a dim light bulb. So
Sure,
it's
sure,
like
sure. So, and but the other thing is not quite following. So, what topology do you mean is non-trivial? What exactly do you mean?
Um,
What do you mean by that?
mm, mm, I mean that the connection that if you represent it as a manifold, it's non-local. So like we have not only this, but we also have like this.
Non-local connection. Okay, so it's not the
Yes,
topology in the sense of mathematics, but the topology in the sense of graph theory, I guess. Like,
yes,
yes.
yes,
Yeah.
precisely.
Yeah.
So Um, from the perspective of the brain scans, if we take MRI or CT, for example, brain activity can be described by state vectors. So, like we measure the level of brains of signal in different brain sections. So we segment the brain into M sections, for example, and we measure them and we take slices at different time. So we get a matrix of vectors of m vectors with n elements. So n is different time moments and m is different brain sections. But then now, if if we presume that there are correlations, this means that efficiently this matrix contains less information than it seems to be. So the real number of degrees of freedom is smaller.
So,
Then
I'm sorry. One more question. So, those x1 are the m-dimensional vectors? Is that what you mean? This x1?
yes, yes.
Okay, so this X is a tensor. It's
Uh,
M by N matrix.
yes, so all these are we have m vectors with n elements, so they form a tensor
I see. Gotcha.
precisely.
Gotcha.
Mm, mm. So efficiently, the number of degrees, if there are correlations, this means that the number of degrees of freedom should be smaller.
Hmm.
And therefore, we need to apply something like something similar to convolution that's done in signal analysis to uh, in order to map this manifold with of m dimension to a lesser manifold with only so this n degrees of freedom to a lesser number k of degrees of freedom. Mm, for this purpose, we introduce a k function it's, from f1 to fk, so each of which takes um, mm, this m-dimensional vector at each time moment as an input, and this gives us dimensional reduction that we need. Now, the correlations are expected to be local, so the map is expected to preserve locality of correlations. So the postulate is that these functions minimize this functional. So the gradient square of fi should be minimal because so if these functions preserve locality, if two xi's that are not too far from each other do not produce values of f that are too far from each other, then this means that this gradient should be small. Then by integrating by parts, we obtain this expression. So we have the Laplacian, and then we can decompose. So if we take a specific class of functions that are L-square integrable, so they have so they do not diverge at infinity, and their squares are integrable, then we can decompose them into eigenfunctions of this Laplacian. And
So
then,
I'm a little bit lost here. So
okay,
is M a dimensionality, or M is the number of regions? Yes.
yes, yes,
Yes. Okay. So there is no time variable here, right?
here no, here
No.
no.
What does a subscript I indicate?
Uh, the subscript I mm, mm, is this is the number of function we take k functions that is smaller than m. Because we want a mapping from an m-dimensional surface to
Okay.
a
Sure.
k-dimensional
Sure.
surface.
No, those functions are kind of predefined functions, or it's like modes, right? They're like modes, no?
Yes, in a sense, yes.
Uh,
Like,
they're not degrees. Are they degrees of freedom? Are you trying to decompose into the? Uh, so I'm completely lost, I think, here.
okay,
So
okay.
let's go to the next slide. Maybe it will clarify here. Uh,
Uh, so, so okay. So now what we take is now. So now the point is that um, mm, mm, so the Laplacian operator by definition has eigenfunctions, and then we get this. But then we need to define the properties of the
well,
manifold,
that's what
which
I'm saying. So equation 4 is only valid if f is eigenfunction of the Laplacian operator. So it has to be kind of a mode function. Like,
exactly. That's what I'm saying. I'm saying that I'm saying that we choose them as. I mean, if we have a generic fi that is L square integrable, so then then we can decompose it into eigenfunctions of the Laplacian operator.
okay. And are you saying here that you also sum over I, right? Summation over I.
No summation. We just take one of the fi's.
One of the eigenfunction of the Laplacian operator, you're saying.
Yes, yes.
Um, okay. And you assume it's a solution of the Laplace. Okay, fine.
Okay. So now our next point is the heat equation. So the point is that we need to define the properties of the manifold in some way, on which this on which these functions sleep. So the properties, so the eigenfunctions depend not only. So the eigenfunctions of the Laplacian depend on the properties of the manifold,
Hmm.
which these functions live in. And therefore what they do is that they start with the heat equation. So for the heat equation, the solution has this form. It can be written, expressed through the green function. And now the green function is approximately Gaussian. And as t approaches zero, the green function approaches the delta function. So now, if we take the initial value of u to be one of these eigenfunctions,
Hmm.
then we get then what we get is that the Laplacian of f is equal to u at the point of at the time point zero. So this is a different time. This is not the time from the data image and the time moments. This is just the so here we introduce time as a sort of mathematical trick.
But hold
Mm,
on, this is a time evolution. You're talking about this field
uh,
F.
uh, yes, yes,
So
but
so it is something that can be checked against imaging and see whether this.
no, no. Oh, this is the uh, um, uh, one. Let me finish. So for now, uh, for now we can using the definition of the derivative as the time variable goes to zero in this limit when it approaches zero. Oh, we get this. So we get this integral minus f at mm, 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 I'm sorry. It should have a time derivative. So time derivative of u
Mhm.
because of this. So we should we take this integral minus this integral at time point zero, which is just f, because this is the initial value
Mhm.
of function at time moment zero. And then we can write this expression in the discretized form, so we get this. And now, as the Laplacian of the constant function is zero, so like if the function at xi and xj is all the same, then we get this. Then we, I mean, if xj is equal to fxi, it means that it doesn't change. It means that the Laplacian is zero. And then from this we get that this expression is equal to this constant. And then therefore after rescaling we get after rescaling mm, we get this. So then then the weight matrix is expressed in this way. And so it's short range, and it means that the correlations larger than some small scale quickly fall off to zero. So mm, this is it.
But hold on, can you go back?
Yes, yes.
the weight elements in equation 11, they're time dependent, and they just what we are having here. We have evolution of this, I mean, a probability distribution in the space X, given by the this Gaussian random jumps. And then as you increase t, the jumps, become larger. And then if you decrease it, then they become more like delta function.
Yes, but so we approach of the limit of when t goes to zero, and so because we discretize it, we replace it with with
Fine,
some
fine.
sigma
So,
square.
but then you're just having a diffusion-like process
Yes,
in the discrete time step described by the discretized heat equation in that space. So you start with some
precisely.
initial conditions and then system evolves. So are you saying that the evolution of signals in this brain evolves according to the
No, this is the next point. So now
okay?
this captures the local phenomena. So
Yes,
the
yes.
uh, but now our next step is the following. Now, what if we do the same for the Schrödinger equation? So instead of the heat equation, we take the Schrödinger equation. So
Why?
effectively, it corresponds. We will see. So
Okay.
because like when we take we now make the mathematics are precisely the same, but now we have to Wick
Yes,
rotate it. So we replace t with it, and
yes.
now we get this, and now the our weight matrix has this form. So now it's long range. So it oscillates quickly, but it never completely decreases.
So are you saying that the reason for introducing the complex I in there is so that it would be non-local?
Yes, precisely.
But it's not only that. I mean, U becomes, before U could be interpreted as a probability distribution. Now U is not a probability distribution. What is U then?
Uh, mm, mm,
I mean, before it was clear how to measure this F. It was like probability distribution. I think that's what they meant. Probability distribution. It was a Fokker-Planck diffusion equation. So it was probability distribution of measuring certain state of brain, m-dimensional state of a brain. And so you're saying it's diffuses. And now you're saying you're adding I to it. So this state is no longer diffuses. It starts behaving according to this equation. And so I think what's missing is an interpretation for what is U now. U is no longer a probability distribution.
well, the point is not what U is, but what F is now. So I mean the F still. So what they do, honestly, I had questions about it.
Hmm.
What they do is that they take
But hold on, U
this
is
weight.
not the same as F? U is not the same as F?
Uh, uh, mm, no, U is U at is the same as F at time point zero. So like
Okay,
it's a
fine.
mathematical principle.
F is initial condition. Okay,
Yes, yes.
then
So
then you
like
evolve F. F
yes,
describes some probability distribution, and here you have, in the Fokker-Planck case, you have probabilities of jumping from one state to another. So that I understand. Uh, but once you put an I there, everything changes. Now you cannot be interpreted, or F, okay,
so,
cannot be interpreted as a probability distribution.
but what they do, I was wondering about that also, is that they take this matrix, this weight matrix, to the power t, and then they take the square modulus of it, and then they use it to evolve the f's. So they diagonalize it and they use it in their algorithm to evolve the f's. This is what was. I
Well, I
also
mean, I don't understand the reason of putting an I there, and so I don't understand also there is no squaring the, so what does it mean, right? So you have, now instead of W, you should have some kind of unitary operator there that changes your state. So if you go back, right? So what is this?
Mm-hmm.
What is, basically you have the unitary operator that changes the wave function f of state vector from one time to another. And then
Mm-hmm.
just taking this unitary operator and squaring all of its components. I mean, this is what 14 is. Yes?
Yes,
It's a, it's
yes.
a, it's a, it's a unitary operator multiplied by the state vector f. Um, so, and it changes, or no, it's Hermitian. Well, one or another, because this is a discrete time steps. Is it discrete time steps here?
I yes.
Yeah,
So
so
we
I think
take
it's a Hermitian
y-
operator.
yes.
But anyways, I mean, what's the point of taking, like, you take Hamiltonian matrix and square its elements? What's the point?
Mm, mm, I was honestly I was wondering about this as well
Yeah.
because we can turn to the paper now because honestly I had this
Okay, but it's okay. It's okay. So, but the point they're trying to make that is, since you
um,
wanna model non-locality, let's model
so yes,
to the
their
Schrodinger.
point is that their point now is that when they apply this to the brain, they get better fits to observational features than the real valued harmonics that are local.
Okay, and that is using equation 16, right? So,
I yes, yes.
okay, so it isn't really about Schrodinger, Schrodinger equation, because it's, you're really doing something strange in this equation.
Yes, it's not like real quantum mechanics. It's like effective, but
I don't think
honestly,
it's
I
even
would.
effective, because you just take some complex valued matrix, which is probably a Hamiltonian, and then you square all of its elements. Uh, I don't know what that actually means.
Mm-hmm. Mm-hmm.
Because that's what it is, Wij is an element of the, um, yeah, I don't know what that means. Okay, but they claim it better reproduces the experimental results concerning the brain dynamics or something like that. Yes.
Yes, yes.
Okay. Well, interesting. Let's see if there are any other questions. Have you seen any other papers that try to, I mean, I'm interested to see if there are papers where actually they model the dynamics or of brain dynamics, like effectively, fine, as a field, fine, but have you seen anything else, or this is as far as it gets?
Well, they compare so they model the dynamics with this algorithm, and they compare it with data on awake and sleep phase, and they find some.
But what
Uh,
is exactly they comparing? I mean, what is the experimental results is there like any plots they make or something that actually
I guess.
like shows something with the Fokker-Planck equation and something with the
Uh,
squared of elements?
with the equation precisely, honestly, I mm, mm, let me show what they plot
Yeah,
actually.
are there any plots?
It's so like
Oh, so they have many plots. Okay. So what is it? What are we looking at?
So right now we're looking at this they vary in the global coupling parameters, optimal fit into the empirical Kuramoto metastability
I
blue
mean, in
curve.
graphs like A graph, B and C graphs. So what is the horizontal line? The
Mm,
global coupling parameter. Okay. Well, I guess we have to look into this closer to understand.
yes.
Okay. Well, anyways, that was interesting to see that people are using Schrodinger equation for something else. Thank you. Thank you. Kirill, are
You're welcome.
there any other questions?
No, I was just thinking that um,
Go ahead, Diego.
maybe it has nothing to do with Schrödinger just because you added like a complex phase. Maybe that just gave more like degrees of freedom for the thing. Um,
Well, it looks like the only reason for them is to use the Schrodinger was to make sure that the something they call this weight element isn't going to zero in a faraway place. That's kind of the only motivation as I see. So there is some kind of notion of non-locality. But this non-locality is not even in the space of regions where the brain regions are, in the space of states, right? So this is you have M regions of brain that you're monitoring. So this is, and then there is a state vector X, and the locality means that the system can kind of go in a very distinct states, other than just diffuse it usually. So if the only reason for you is to get some non-local transition probability, then there are other ways for you to write it. You can just, instead of Gaussian weight matrix, you can model it as a power law. Then you wouldn't need any Schrodinger equation, and you'll right away have this non-locality. So, but I don't know. I mean, there may be some other deep reason for that I don't understand. Okay, well,
Okay.
thank you, everyone. Thanks, Kirill, and I'll see you guys next time.
Okay.
uh,
Okay.